Good afternoon, class. Today this is a pretty painless assignment. We'll be looking at operations on functions, difference quotients, and composition. Really, it's all pretty much just function notation. And let's see, let me get there. Let me write out a little bit there. So let me see. We're going to start off by looking at operations on functions. And by operations, I mean the real number operations of addition, subtraction, multiplication, and division. The usual operations we think of related to real numbers and the real number system. Operations on functions is exactly what you would think it is. It's just function addition is algebraic addition. Function subtraction is algebraic subtraction. There's just one little line of notation. Function multiplication is just your standard algebraic multiplication. Likewise for addition. You'll see what I mean when we look at number 1. There's really not new algebra here, just the notion of how they're expressing these ideas. Number 1, they give us the function f of x equals 2x plus 3. No, 5x plus 3. They give us the function g of x. G of x is 4x minus 7. And they ask us to find, look at this notation, f plus g of x. That's saying take f of x and add it to g of x. Well, we know how to add a binomial to a binomial. Well, subtraction, f minus g. Oh, we have a minus in front of all of that stuff. I bet we're going to have to distribute a minus. Multiplication, well, we'll discuss how we're going to multiply and divide in a moment. I think I'm getting ahead of myself. The first thing they want us to do is find f plus g of x. Also, once we find all of those, they want us to give the domain. So we'll start with f plus g of x. F plus g of x. That's saying take f of x and add to it g of x. So we're going to have f of x plus, we're going to have the function g of x. For f of x, we know f of x is 5x plus 3. They gave us that function. It's just a 5x plus 3. And I'm going to enclose that 5x plus 3 in parentheses just to make the point. That stuff there is what came from f of x. They gave us 5x plus 3 for f of x. And we're going to add that to g of x is 4x minus 7. So I'm going to enclose that 4x minus 7 in parentheses as well. Just to make the point, these two terms came from g of x. Those first two terms came from f of x. Now looking at the parentheses, there's nothing in front of those parentheses, in front of 5x plus 3. They're an unnecessary set. We don't need them. I'm just going to drop them. Looking at the second set of parentheses, there's a plus in front of them. Well, that's like a positive 1. So we're going to have to distribute through a positive 1. Is that going to change anything? No, it'll just stay a 4x plus 7. In a moment, in place of this red plus, we're going to have a red minus. So, oh, I forgot to turn on my microphone. There. So in a moment when we have that minus there instead of a plus, we're not just going to be able to drop those parentheses. Be thinking about what we're going to have to do. But for this one, with the plus in front, it's an unnecessary set of parentheses. When class started today, if I'd given you 5x plus 3 plus 4x minus 7, you would have known, okay, those parentheses are unnecessary. You can just drop them. The second set, there's a plus in front, so there's nothing to distribute through, so other than a positive 1. So we just drop them. And now it's just a matter of combining like terms. Addition of functions is nothing more than algebraic addition. You know how to add algebraic expressions. You combine the like terms. 5x plus 4x says we have 9x's, and 3 minus 7 gives me a minus 4 for my first answer of 9x minus 4. Any questions there? 9x minus 4. And now the next one, we want f minus g. F minus g, let me write that down. F minus g. Well, following this pattern, it's f of x minus g of x. I don't think we need to write it out in terms of f and g. It's 5x plus 3. And notice I'm enclosing the 5x plus 3 in parentheses. That's saying that's all the stuff I got from f of x minus, then g of x is that green 4x minus 7. Subtraction of functions is just your usual algebraic subtraction. To subtract algebraic expressions, you remove the parentheses. Well, that first set of parentheses there is unnecessary. As I said, there's nothing in front to distribute, so it's just a 5x plus 3. But here's what I was warning you about. We have a 4x minus 7 with a minus in front of it. What are we going to have to do? Okay, so that minus, it's like distributing through by a negative 1. That positive 4 is going to become a minus, and the minus 7 will become a plus. And now it's just a matter of combining like terms. The standard algebraic subtraction, 5x minus 4x, gives me 1x, and what's my constant term going to be in the answer? 3 plus 7, I agree with a positive 10. So x plus 10. There, x plus 10. Any questions there? Pretty painless. Now we're ready for f times g. Notice it's just fg. They don't put a dot there for multiplication. If you don't see an operation, you assume the operation is multiplication, and that's the notation they're using here. Just fg times x. That's saying to take f of x, we're going to take f of x. That's 5x plus 3. And we're going to multiply it by g of x. G of x is 4x minus 7. Oh, thank you. I forgot to switch. Thanks. So, f of x is 5x plus 3. G of x is 4x minus 7. And just like I did a moment ago, I put the f of x in parentheses and the g of x in parentheses. If we come in here, and I just wrote this up on the for the class, what would we have to do? Be more specific. FOIL it out. You take the 5x, you distribute it over the 4x minus 7. You take the next term, 3, distribute it over the 4x minus 7. So I call that the FOIL method. So, as I said, algebraic multiplication and function multiplication are the same thing. It's just a matter of what does this notation mean. It means take f of x and multiply it by g of x. But the algebra part is nothing new. First, 5x plus 4x gives me a 20x squared. Outer. I agree. Inner, 3 times 4x. 12x, and last. Okay. So we have 20x squared, negative 35x plus 12x. Is that a minus 23x? And a minus 21 for our final answer. Function multiplication is just algebraic multiplication. Take whatever f of x is and multiply it by g of x. Oh, let me type that in. 20x squared minus 23x minus 21. 20x, use the little hot button exponent key, they call it a superscript, minus 23x minus 21. Any questions? Generally, what's the worst operation? Addition, subtraction, multiplication, or division? Division, okay. F divided by G of X. They're using a fraction bar to represent division. That means you take f of x, they told us f of x, 5x plus 3. That's what's on top. We're dividing it by g of x, 4x minus 7. And this is one of those rare times, oh goodness, I can see, I'm just going to keep at that. F divided by g of x. F of x is on top. G of x is on the bottom. If I could factor these things, I'd try to factor and cancel out a common factor. But are these things factorable? They're each linear factors. There's nothing we can do to reduce that. So this is one of those rare times where the division is the easiest one of all. Just 5x plus 3 on top, 4x minus 7 on bottom. Oh, goodness. So I'm clicking there. I get my hot button. If my fraction, if I'm having to enter the fraction, say 1 over 2, just one term over one term, I don't bother with the fraction hot button. I just use the slash on my keyboard. But if you have anything other than just number over number, one term over one term, to make sure you're typing in what you want to type, I would highly recommend that you use the fraction hot button. On top, we had a 5x plus 3, and on the bottom, we have a 4x minus 7. Any questions there? Now the real work begins because they want the domain of f plus g, f minus g, and f times g. Well, they don't ask us for the domain of f and g, but just for the record, what would they be? F and g. What would the domain of f of x be? What about the domain of g of x? I'll tell you right now, the domains are the same. I'm looking at a paragraph here. Hold on. I went back to last week, and I'm going to look at a paragraph down here. Now, unless told otherwise, assume the domain of an algebraic function is the set of all real numbers that, when substituted for x, produces a real y value, not an imaginary number, not a denominator of 0. You want to avoid square roots and negatives. You want to avoid denominators of 0. And what did Dr. Sheen tell his class 33 years ago that I thought was such a good statement? If your function has no square root symbols, no fractions, unless you're told otherwise, you assume the domain is all real numbers. So when I asked earlier, I asked, what's the domain of f and g? What do y'all say? Negative infinity to positive infinity. Now, so as we look through these operations, we need to ask ourselves as we go through, is there anywhere along the way that we picked up a square root or a fraction? Because if so, then we've got to take that into consideration. F plus g, no, I just see linear terms and constants. So no fractions, no square roots anywhere through that work. I'm looking at the work for f plus g. No fractions, no square roots, so the domain is all real numbers. What about f minus g? Look through there. You see any square roots, any fractions? No. So that you assume the domain's all real numbers. What about f times g? All real numbers. Once again, we didn't pick up a square root or a fraction. So f plus g, f minus g, and f times g all have the same domain, all real numbers. That's why my brother's always saying they need to put in a minus infinity to positive infinity hot button. I haven't listened to him at Pearson yet. I think when they get his recommendations, they're going, oh, it's one of them crazy Precella twins, and just sort of throw them in the, or hit delete. There. And I'm going to do something. I'm going to copy and paste this just to save me a few seconds. So f minus g, paste it in. And f times g, paste it in. Now for f divided by g, it's not going to be all real numbers. Let's look back at what we have here. We want the domain of f divided by g. Well, there's no square root, so it's not going to create imaginary numbers, but there is a fraction. What do we not want to have happen? What do we not want to have happen when dealing with a fraction? So to find the domain, this is called a rational function, just some terminology. I don't know if I've mentioned it or not. A rational function is this. A rational number is any number that can be written as a fraction, and a rational function is any function that can be written as a fraction. Remember that little thing, n over o. No, you don't want a denominator of 0, so 4x minus Oh, 4x minus 7 cannot equal 0. So 4x cannot equal here. No, I have the 4x on the left side. I'm moving that over. We get 4x can't equal 7. And then divide by 4 to get the x cannot equal. There's the 7 over 4. But they're not going to let you write that out like that. I'd prefer it if we wrote out all real numbers except for 7/4. You can plug any number you want to in there for x except for 7 over 4. But they're not going to let us write it like that. We're going to, here's the number line. Think of a number line. This is like a denominator cut point. You don't want 7/4, but you can have anything else there and there. So how are we going to say that using interval notation? Think of what we were doing. Can we just do one interval from negative infinity to infinity? No, it's got to be two separate intervals. Are we going to have any rectangular brackets in our answer? No, there's no closed circle. So I'll write out the left-hand interval. Parentheses, negative infinity, comma, 7/4, and a parenthesis. Or you call out the right angle for me.
7 over 4, comma, infinity.
And in front?
Right.
Okay, good. Any questions there? Realize that there's really not been any new algebra here. All that's new is just that notation. What does this f plus g, f minus g, f times g, and f divided by g mean? The algebra itself, even finding the domain, it went back to what we were doing a week ago when we were looking at functions and domains for the first time. But here I gotta go, parentheses, negative infinity, comma, 7 over 4. They're typing 7 over 4. That's when I just use the little slash. If it's just number over number, I'll use that slash. Otherwise, to make sure that I'm typing what I want to type, I use the fraction hot button. Any questions there? Okay. Difference quotients. There. And for operations, there's not that much. There's that one problem with, 8 parts. There's that one problem involving operations. That's it in the homework. The next topic, difference quotients. The difference quotient is defined to be the following fraction. It's f of x plus h minus the original function f of x all over h. And that's an important piece of the definition of derivative. If you have to take a calculus class, you'll see that this thing here is part of the definition of derivative, and derivatives are the basis for all on which all calculus is built. So we don't have to worry about the calculus portion and the calculus application of this difference quotient. All we have to do in this class is simplify difference quotients. what I'll do when I'm simplifying a difference quotient, I'll break it into 3 pieces. Usually the longest piece will be finding f of x plus h. Then I'll subtract off the original function they gave me, and whatever's left, the last step will be this division by h. This is not that bad. Let's see, let's look at number 2. They give us the function f of x equals x squared minus 8. This is number 2. And they give us f of x is equal to x squared minus 8. Notice how they're splitting it into 3 parts. First of all, they're finding f of x plus h. Then they're going to simplify the entire numerator by subtracting off the original function. And then in the last step, they perform the division by h. Those 3 steps, that's what I do whenever I'm simplifying a difference quotient. Look at number 3 real quickly. They don't break it into 3 steps. All they want is that final answer, f of x plus h minus f of x all over h. They just want the final answer, but even when we do number 3, I'm going to break it into the 3 steps that they're using here in number 2. Okay, so the first thing, f of x plus h, it's just function notation. There are plenty of math textbooks that put difference quotients into this, that section with functions and function notation. So this isn't any new algebra, and you'll notice for the problems on the homework and on the test involving difference quotients, they'll remind you, they're going to show, oh, f of x plus h minus f of x all over h. So you don't have to memorize that, what that the difference quotient is, but you do need to remember the 3 pieces and the way we're going to be breaking this up. First of all, they want f of x plus h. That's part A. Let me switch over. Okay. F of x plus h. This is part A. I want f of x plus h. F of x plus h. We know how function notation works. This says go to f, and wherever you see a variable, replace it with what's in the parentheses. So I come up here, and I'm going to be replacing, in place of that single blue x there, I'm going to have to write in an x plus h. I still have that square and the minus 8. X plus h squared. I'll tell you right now that it is not x squared plus h squared. We've run into this problem before in other sections. I remember we were having to square a complex number in the second assignment, if I remember correctly. What am I going to do to square a sum? To square a sum or difference, it's not just x squared plus h squared. Here's my scratch paper. We have x plus h quantity squared. I'll give you a hint. This means write it out twice, x plus h times x plus h. What are we going to have to do to perform that multiplication? FOIL it out. X times x is x squared. X times h is xh. Here's my advice to you. If you have 2 different letters in the same term, put them in alphabetical order. That makes it easier for you to spot like terms. X times h, I'm going to write it as hx. What's my inner product? Oh, this is my scratch work right here. But first, outer, what's the inner product? Another hx. Hey, we have like terms. If you'd written this as an XH and that as an HX, you may not have noticed that you could combine them. That's why I say if you have two different letters in the same term, always put the letters in alphabetical order. Makes it easier for you to spot the like terms. And what's last times last going to be? H times H is H squared. So that reduces just to X squared, HX plus HX, 1HX plus 1HX. We now have 2 HXs plus H squared. Any questions on my logic? You know, today, everything looks black to me. I can't tell the difference between the blue and the green. Does that help? No, it doesn't help. All it does is make it flash, blink. Now, I'm going to turn that on. Can y'all tell the difference that this is green and right there is blue? Yes? Oh, good. Just my poor vision, I guess. X plus H squared, we know that that's X squared plus 2HX plus H squared. We just simplified that on our scratch work. But what have we got tacked on here? That's not all of f of x plus h. We have something else left over, that minus 8. Any questions there? The first thing we did, f of x plus h, and generally this is the longest piece of the problem, okay? These are for polynomials. And now for part B. Part B, they want us to take the f of x plus h that we just found. We just found f of x plus h. And they want us to take away the original function f of x. If you understand what they're asking for, this B part here, you can do without showing any work. That's saying, take what you found in part A and take away the original function. This minus is working. Isn't that the way you all learn subtraction? 5 take away 2 was 3. This minus here is working like that old-fashioned arithmetic minus of take away. Here's what we have, f of x plus h. That's part A. This is part A. And we're going to take away f of x, that's the original function. So we have this stuff here. We're going to take away, and we're going to take away the x squared minus x squared. What else is going to be dropped off? Take what you found in part A and take away the original terms. So what else? X squared minus x squared is gone. There's something else that this thing has in common, that this answer has in common with the original function. What is it? That negative 8 minus a negative 8, that becomes a negative 8 plus 8. The only thing you're left with is 2hx plus h squared. Take what you found in part A and take away the original function. I think of myself as an optimist because no matter how bad a day is or something is, I always think to myself, well, things could be worse. And here's something you could think of. Suppose instead of a square, that had been a cube. If that had been a cube, we would have had to have 3x plus h's. Once we were through with the x squared plus 2hx plus h squared, we'd have to distribute another x through all of that. We'd have to distribute another h through all of that. Combine like terms, put them in descending order based on the variable probably x to give you an x cubed plus 3hx squared plus 3h squared x plus h cubed, if I'm doing it correctly in my head. But the point is, we should be grateful. They're not going to have any where you're having to cube the x plus h, but you will have to square it. So remember how we came up with that, okay? But there won't be any where you have to cube or, heaven forbid, raise x plus h to the 4th power. So let's see. Well, I didn't write in the answer for the first one. I better write that in. What was that? X squared plus 2hx plus h squared. And I still had that minus 8 stuck on. Oh. And once we took what we just found and subtracted off the original terms, we were left with 2hx plus h squared. For any polynomial function, it doesn't matter how many terms it had. There could have been a 7x squared plus 4x minus 8. For any polynomial function, once you perform that minus f of x, the only thing you better be left with are terms that have h. Everything that doesn't have an h has to subtract off if you're doing it correctly. And sure enough, we were left with a 2hx plus an h squared. Now they want us to take what we just found and divide it by h. So part C, we're going to take what we just found, f of x plus h minus f of x, and divide it by h. So we're going to take what we just found, that's a 2hx plus an h squared. Divide it by h. Rather than putting it as all one fraction, I think the division is easier if you do that. Now, if the denominator weren't just an h, you wouldn't want to do that, splitting it up like that. But for the difference quotient, the denominator is always going to be an h. And remember I said in part B, you always have to have an h term remaining, so you'll always be able to cancel an h. We can cancel an h there and there to give us a 2x plus, what is this fraction going to reduce to? We have two h's on top and one factor of h on the bottom. What can we do? Okay, so cancel an h above and below. There's my final answer that we're looking for. In a calculus environment, we would then start asking ourselves, what happens to that algebraic expression as h gets closer and closer to 0? But we don't have to worry about that. Our answer that we're looking for is 2x plus h. So we come here, 2x plus h. Any questions? For the difference quotient problems, they will remind you of what the difference quotient is. They'll show you that it's that fraction there, okay? But for something like number 3, the function is definitely messier. It won't be that much messier, I suppose. At least it's just an x plus h that we're going to have to square. And we've already done that. It's written there on our scratch work. I'm still going to split it into 3 parts. Let me write this function down. Let's see, this is number 3. We want to find f of x plus h minus f of x all over h. And they give us that the function f of x is 3x squared plus 7x plus 4. the first thing I'll do is the f of x plus h. That's like the little a part here on number 2. I'll do that first. F of x plus h. That says go to your function f, and everywhere you see a variable, you're going to replace it with what's in the parentheses, x plus h. So we're going to have to replace 2 x's. Replace the variables with the green x plus h. So we have 3 times x plus h squared plus 7 times x plus h plus 4. And I'm staring at x plus h times x plus h here. We know it's reduced into x squared plus hx plus h squared. So there it is. That's 3. I'm going to replace the x plus h squared with the x squared plus 2hx plus h squared. I'll do all the distributing in a moment, all in one step. X plus h times x plus h became x squared plus 2hx plus h squared. And we know what we have to do here to get rid of these parentheses. The first set of parentheses has a 3 in front of it, so we'll distribute the 3. That'll give us a 3x squared plus the next term, 6hx, just making sure y'all are awake, plus 3h squared plus here, we're distributing the 7 to give us the 7x plus 7h, and we still have a plus 4 there. Correct. We don't have to type all that in, though, at least. Now, the second thing we do, we subtract off f of x. My b part, I take I'm simplifying the entire numerator. I'm taking f of x plus h, what we just found, and subtracting off the original function. If you understood what I said earlier, you should know what f of x plus h minus f of x is going to equal. Or you should know which terms are going to disappear. Let's take it from that approach. Which terms are going to subtract off? Which terms will subtract off? We have a 3x squared minus a 3x squared. So the 3x squared is gone. What else? 7x minus 7x. That's gone. Anything else? The 4 minus 4. Everything that's in the original function has to appear in f of x plus h if you're doing this correctly. It has to appear there, and then you can just subtract it off. So in the next step, the only stuff that's left is the stuff that has what letter appearing? H. The 6hx plus 3h squared plus 7h. Any questions on our logic? You take what you just found and take away the original function. The last thing we do, part C, that's when we divide by h. Part C is the division by h. So we're going to divide by h, divide by h, divide by h, divide by h. And remember I said every term has to have an h. So h divided by h is canceled, leaving us a 6x plus here. H cancels above and below to give me 3h plus, okay, the h's cancel out completely, and all you have to type in is 6x plus 3h plus 7. Any questions there? 6x plus 3h plus 7. 6x plus 3h plus 7. Oops, is that it? Any questions there? Been going and going. 45 minutes. We've gotten 3 problems done in the first 45 minutes of this video. Wow. Huh. Okay, the third topic. This stuff will start going faster, okay? Composition. Oh, goodness. Let's see. Okay. Composition of functions. Composition of functions. In addition to the usual operations on real numbers, addition, subtraction, multiplication, and division, there's an additional operation that's only applied to functions. You can't just apply it to real numbers. It's called composition, and they came up with they had to have a little symbol. We represent operations with symbols. If there's no symbol, then we assume the operation is multiplication. So they had to come up with something to represent this operation. And here's what they came up with. F composed with the G of X. The little symbol between the F and the G is a little O. That's defined to be F of G of X. Composition is just repeated function notation. We know how this function notation works. This is saying, go to f of x, and every time you see a variable, plug in the other function, g of x. Suppose the g were first. G composed with f of x. That means g is on the outside, and f of x is on the inside. That's saying, this notation says, go to your function g, and wherever you see a variable, substitute f of x. That first representation, f is on the outside. That says, go to f, and everywhere you see a variable, substitute g of x, whatever g of x is. Well, we're going to evaluate compositions at numbers, and we're going to evaluate them at variables. So the first one, number 4, they give us 2 functions. F of x is negative 3x minus 1. I'll say f of x is negative 3x minus 1. And, oh, it's not g, it's h. H of x, they can use any name they want to. I suppose h is better because we don't have those tails down there running into the lines. H of x is negative x plus 4. That's a negative x plus 4. I miscopied. Negative 3x minus 1. They want us to find h composed with f of 5. That's where I was getting that 5 from. So they want us to find h composed with f of 5. H composed with f of Let's write this operation without the little o. We're going to write it just using parentheses. That says h is on the outside, f of 5 is on the inside. The function that's written in front of the O is on the outside. F of 5 is on the inside. Look inside those parentheses. Just ignore the H for a moment. F of 5, we know what that's saying to do. What is that saying to do? You go to your function f, and wherever you see a variable, you're going to plug in 5. So you're coming up here, you're plugging in 5. Negative 3 times 5, that's a negative 15 minus 1. Negative 15 minus 1. What's that giving me for f of 5? Negative 16, I agree. We still have that h sitting outside there. All we've done, I said this is repeated function notation. First of all, you had to deal with the f of 5. Go to f, plug in a 5. Negative 15 minus 1 gave me a negative 16. Now, what's this notation saying to do? You go to h, and wherever you see a variable, you plug in negative 16. Watch all those negatives. You have that green negative right there. It's hard to tell it's green, but it's green. You replace the x with negative 16. And what else do we still have there? We still have that positive 4 right there. You plugged in the negative 16. The opposite of negative 16, what's that giving you? 16 plus 4 for a final answer of 20. I agree. Okay, so we come over here. Final answer of 20. Any questions there? Let me put back up my work. You know something? I'm going to make up an example. I'm just making this up. EX for an example I made up myself. I'm going to use the same functions. F of x is equal to negative 3x minus 1. And h of x is still that negative x plus 4. They asked us to find h composed with f. Well, suppose they'd asked us to find f composed with h. Suppose they'd reversed those function names. Would it have all been the same? At 5, would we still have gotten the same answer? In this event, f is on the outside. So f is the one that's on the outside. And on the inside, we have h of 5. H of 5. H of 5. What's h of 5? What are we going to have to do? Okay, so we're going to have a, I'm just going to do it out here in my little scratch work. It'll be a negative 5 plus 4. What's that giving me? I agree with negative 1. We plugged the 5 in, so it became a negative 5 plus 4, which is negative 1. Now we need f of negative 1. What's this notation saying to do?
Negative 1 and 2 right there.
So you have a negative 3. You're going to plug in a negative 1. And we still have that minus 1 right there that we stick on. Negative 3 times negative 1, that's a positive 3. Minus 1, what am I getting? Okay. So let's suppose they ask you to find H composed with F on the test, and you accidentally find F composed with H. You go in the opposite order. Do you expect to get the same answer? Probably not. Occasionally you might get the same answer, but operations are classified as commutative or not commutative. For example, addition is commutative. A plus B always equals B plus A. What about subtraction? I'm going to commutative and not commutative. Commutative and not commutative. A plus B always equals B plus A. So addition is commutative. What about subtraction? Does A minus B always equal B minus A? No, it usually doesn't. So that's not commutative. What about multiplication? A times B, does that always equal B times A?
No.
I think it does. Yeah, I think if you reverse the order of the factors, the multiplication will still be the same. Multiplication, I will say, is commutative. But what about division? Now, 6 divided by 2 sure doesn't equal 2 divided by 6. Division is not commutative. Now we have this new operation. My brother calls these operations fog and golf. But that name only works if you use an F and G, okay? But they'll call it fog and golf. So, that's one of those things that annoys me. And he knows it annoys me. And so he'll say fog and golf just to annoy me. And I'm a lesser person because I shouldn't let it annoy me, but it does. And I don't know why it does. It's meaningless. Why should it bother me? Fog and golf. I don't know. It does. But let's go back to this fog and golf stuff. Is composition of functions commutative? Well, H composed with F always equal F composed with H. I think we see our answer right there. Not commutative. Not commutative. And any questions before we go on?
Another way of saying that, and then we just put composition in there.
I can't hear you.
What's another way of naming that circle we just put in the not commutative? Should I call that?
Addition is commutative. Subtraction is not commutative.
Maybe just wrote down the O.
The O.
Should I call it commutative? Or can I call it composition?
Yes, composition. That's the formal name of it. Yes, composition, function composition, or composition of functions. And let's see. The longest part of this problem is going to be writing down the tables. So this is number 5. They're using tables here to represent two different functions, f and g. 3 is assigned to 6. Do y'all see how they're creating? Basically, it's ordered pairs. 3, 6, 5, 3, 8, 4. Y'all see that these things are assigning the x values to the y values. So there's f. Now g. Let me write g down. with g of x, 7 is assigned to 5, 2 is assigned to 3, 10 is assigned to 8, and 20 is assigned to 21. And they want us to find f composed with g of 2. F composed with g of 2. Where? There it is. There. What function's on the outside? I'm about to write this without the little O, so what letter am I going to write first? F of g of 2. Even though you write f first, you use the inside function first, okay? F is what's written first, but you work from the inside out. G of 2. Go to your function g and tell me what number 2 is assigned to.
3.
Go into your function g, 2 is assigned to 3. I agree. We still have that f sitting in front. Now we want f of 3. That says go to my function f. What number is 3 assigned to? Be careful. Each time that number in the parentheses is acting like x. So go into your function f. 3 is assigned to 3 is assigned to 6. You don't come down here to the 3 and assign it back to 5. That number there is now acting like x. X, the function f, assigns 3 to 6. That's why I said it'd take longer to write down the tables than to answer the question. Any questions there? Using G, 2 is assigned to 3. Then using F, 3 is assigned to 6. So, final answer of 6. Number 6, it's another problem with tables. Hey, look at this. They want us to find f composed with f of 5. What are we going to do with the G table in this problem?
Ignore it.
Just ignore it. I'm not writing it down. I'm only going to write down the f table. Okay, good. Three is assigned to 4 in the F table. 5 is assigned to 8. And 8 is assigned to 6. And they want us to find F composed with F of 5. F composed with F of 5. That's what I was looking at. I was looking at F composed with F. That's what they wanted. They weren't using G. That's why we didn't bother writing down the G table. So this next question should be easy. Which function's the outer function? It's the first one written. F is the outside function. Which function's the inside function? F again, okay. F is the outside and F is the inside. F of 5. Looking at the function, the table F, what number is 5 assigned to? F of 5. 5 is assigned to 8. I agree. Now we need F of 8. Going back to the F table, 8 is assigned to 6. And it's just a coincidence that the answers for both 5 and 6 were 6. That doesn't mean that anytime there's a table, the answer is 6. That's just a freak coincidence. 5 is assigned to 8. 8 is assigned to 6. Any questions there? So, we found compositions at numbers. A composition of two functions, at a number gives you a final answer that's a number. If it's a composition at a number, your final answer is a number. Now we're going to find compositions in terms of the variable x. That means your answer is going to be an algebraic expression in terms of x. You'll see what I mean in a moment. It's not that bad. Don't start panicking. I know how I hate it when y'all start panicking. F of x is equal to 5x minus 10. And g of x is 10 minus 2x. And look at what they want us to find. They want us to find, oh, there's going to be two answers here. They want us to find f composed with g of x and g composed with f of x. So we're going to find both of them, f composed with g and g composed with f. First what I'm going to do is f composed with g of x. I'll be getting my 35-year service pin in May here at this college. From having worked at this college for 35 years. That was one thing about 2020. I wanted that 30th service pin. They canceled the award ceremony because, well, the COVID pandemic. But I've been waiting. I can't believe I'm only, 10 months? Not even that long. 7 months? What is this? October? In about 6 months. I'll do it at the very beginning of May. But anyway, the point is I've learned something from all these years that for composition, the fewer steps, the better. This is saying taking g of x, take the function g of x and plug it into f of x. You're taking g of x and you're going to plug it in over here into f of x. Y'all see what I'm trying to show? I'm taking g of x and I'm plugging it into f of x. The inside one, that's what you start with. You take it, you plug it into the outside one. So we have 5, replace that x with the 10 minus 2x. And we still have this minus 10 here. Now it's just a matter of simplifying this. We know we need to distribute the 5. That'll give me 50 minus. Okay. And I still have that minus 10. Since the 50's first, I think I'll just go 50 minus 10 is 40 minus 10x for my answer for f composed with g. We took g of x and plugged it into f. We took g of x, we plugged it into f for 40 minus 10x. I'm going to go ahead and type that in right now. 40 Now we want g composed with f of x. G composed with f of x. So we've reversed the order of the functions. That's saying take f of x and plug it in to g. Oh, take f of x, plug it into g. You're taking this function f of x and plugging it in to g. Can y'all see what's happening? You're taking f of x, you're plugging it into g, so you have 10 minus 2, and in place of that x, you have that 5x minus 10. I'll reduce it in a moment, but any questions on my logic at this point? It's important you see the order. This is saying take f of x, that second function, plug it into g. Take f of x, plug it into g. So we have a 10 minus 2 times 5x minus 10. Don't distribute an 8. Remember the order of operations, you multiply before you subtract. So you can't subtract that as an 8 and distribute an 8. First thing you have to do is distribute that minus 2 to give me 10 minus the 10x, and there.
20.
And what are we going to get then? 10 plus 20, that's 30. And we have, what else attached? The minus 10x. Good. For composition of functions, if you view an example, they're going to show each little step. They'll write the composition out as f print, like this here. They'll write it out with an x, and then they'll replace the g of x with a 10 minus 2x, and eventually they'll get over here and replace that x with the 10 minus 2x. If I've learned anything, I've learned from my 35 years at Del Mar that for the best results for composition at a variable, do it in as few steps as possible. Did I type in that answer? 30 minus 10x? No, I didn't. 30 minus 10x. Let's do another one. Number 8. Let me write these problems down, these functions down. And number 8. We have f of x equals 6x plus 1. And g of x is equal to the square root of x. Same instructions as the previous problem. They want us to find f composed with the g of x, and then g composed with f of x. So we'll start off f composed with g of x. F composed with the g of x. We're going to take g of x and we're going to plug it into f. So we're taking g of x and we're going to plug it into f over here. So we're replacing that x with the single term, the square root of x. We still have a plus 1 stuck on. And there's nothing else we can do there. Just leave it as 6 square roots of x plus 1. Any questions there? Okay, let's go in the opposite direction. G composed with f of x. That means we're taking, let's see, I'll use, what color should I use? I guess I'll use, okay, I'll use this color. This is take f of x and plug it into G. You're taking f of x, that entire 6x plus 1, and you're plugging it in to G. So you're taking 6x plus 1, f of x, you're plugging it into G, so you have that big square root, and what's underneath that square root? 6x plus 1. For my final answer. Any questions there? So we have 6 times the square root of x. Get out of that, from under that radical before you type the plus 1. Now for this one, what's the first thing I'm going to type? I'll do the square root first, and then everything's underneath it, 6x plus 1. Any questions there? Not too bad. Number 9. Same instructions. They want us to find f composed with g of x and then g composed with f of x. And we have f of x is equal to, it's a square root function with 3x underneath it, and g of x is 1 over x. They want us to find f composed with g add x and g composed with f add x. So we'll start off f composed with g at x. That says take g of x and plug it into f. Take g of x, and we're going to plug it into f, where there's a variable. So that's a big square root. We have a big square root. We have a 3 times, we're replacing that x with 1 over x. And what's 3 times 1 over x?
3 over x.
3 over x. I'm going to insult your intelligence just by reminding you that 3 times 1 over x, that's a 3 over 1 times a 1 over x. You multiply numerator times numerator. 3 times 1 is 3. 1 times x is x. You don't multiply both of them by 3. If you multiply above and below by 3, and I see that happening, especially on tests, 3 over 3x, and it's counted wrong. Any questions? There, okay. Let's go the opposite direction now. We're going to go g composed with f of x. So, g composed with f of x. You're taking f of x and you're plugging it into g. So you're taking f of x and you're plugging it into g. So we have that little green x that's going to be replaced with that square root of 3x. Gosh, this is messy. It's 1 over, replace that x with the square root of 3x. Oh, I forgot to box my previous answer also. Any questions on my logic? I guess just looking at this work doesn't help. You have to follow what I was doing. This text says take g of x, plug it into f. So we took g of x, plugged it into f, replaced that x with 1 over x, and got the square root of 3 over x. Then we reversed it. We take f of x, plug it into g. Take f of x and plug it into g to give me 1 over the square root of 3x. Any questions before I type in the answers? Okay. So, first thing I type is the square root, and then it's just a 3 over x. For the second one, what's the first thing I have to type? I type that fraction hot button, and then on top you have a 1, and on the bottom you have a square root of 3x. You'll remember that at the very beginning of the semester, we were saying, oh, don't leave a square root in the denominator. We multiply above and below by that square root of 3x, and we get the square root of 3x over 3x. But here, there's nothing wrong with a radical being in the denominator. As a matter of fact, if this were a trig problem and I needed to know the reciprocal of this, the non-rationalized form is better than the rationalized form. The reciprocal is what you get if you just flip the fraction upside down. If you had to find the reciprocal of this, with that 1, that's easier. Just flip it over, the square root of 3x all over 1. But either way, they will take it. I think they'll take it in both directions. I mean, whether you rationalize or not. I've never rationalized, so I'm not sure. But surely they would take it if you typed in. Y'all follow what I'm saying there? This one would be, hey, I said similar problem. Isn't it the exact same thing? It is the same thing, isn't it? So we have that square root of 3 over x. Now I'm just curious, if we rationalize, are they going to count it right? If we rationalize, we get the square root of 3x on top, and on bottom, just a 3x. Okay, they took both of them. Any questions there? Okay, number 9. For f of x equals 7x minus 5 and g of x equals 1/7 times the binomial x plus 5, find f composed with g of x and g composed with f of x. Okay, I think I'll put it over here, right up here. Number... This is number 10. We have f of x equals 7x minus 5 and g of x equals 1/7 times x plus 5. Let me make sure I didn't miscopy this. 7x minus... First thing they want us to do is find f composed with g of x. That says we're going to take g of x We're going to take g of x and plug it into f. So we're taking g of x and we're plugging it in to f. Y'all follow my logic? I have 7 times 1/7 times x plus 5. I should have changed colors there. I left it all as black. Got 1/7 times x plus 5. And what else do I have stuck on there? A minus 5. Good. Remember, you multiply from left to right. And so this is going to work out very nicely. You start multiplying from left to right. 7 times 1/7. What's about to happen to those 7s? They cancel out. So all you have is a 1 times x plus 5. 1 times x plus 5 is just x plus 5 minus 5. Oh, this works out very nicely. What are we being left with? Just an x. So f composed with g of x reduces to x. Now they want us to find g composed with f of x. So we're going in the other order. You know something? To make this less messy, I'm going to recopy f and g. F of x is 7x minus 5, and g of x is 1/7 times x plus 5. They want us to find g composed with f of x. Here we're taking f of x and we're going to plug into g. So we're taking f of x and we're going to plug it in over here into g. So I have that green 1/7 times, I have that plus 5 stuck on there. What am I writing in place of this green x?
7x.
Okay, good. Hey, I think this is reducing pretty nicely. -5 plus 5, that's gone. What's 1/7 times 7? What's about to happen to those 7s? So what are we left with? We have a 1 times x, which is just x. These are two very special functions, f and g. 1 week from today, we'll be looking at inverse functions, and we're going to say that if two functions' compositions reduce to x in both directions, then those functions are said to be inverses. That means everything cancels out except for the independent variable x. In that event, we say f and g are inverses, and we'll define what we mean by inverses in 1 week's time. But realize these are very special functions. F composed with g of x, everything canceled out except x. G composed with f of x, everything canceled out except for x. And notice they're asking that question. Does f composed with g of x equal g composed with f of x? Usually the answer is no. Generally, you don't expect that to happen. But in this rare event, yes. And we'll see functions like this in more detail 1 week from today. Any questions there? Number 11, the same instructions. Let's see. They give us the two pairs of functions, find f composed with g of x and g composed with f of x. So number 11. Oh, look at that function. F of x is the cube root of 6x plus 7, and g of x is 1/6 x cubed minus 7/6. Let me make sure I have not miscopied anything. I want us to find, first of all, f composed with g of x, f composed with g of x. That says take g of x and plug it into f. So we're taking g of x and we're plugging it in to f. So we have the cube root of 6 times all of that stuff plus 7. We're replacing that x with 1/6 x cubed minus 7/6. We took g of x and we plugged it into f. And now it's a matter of simplifying. Distributing the 6 over the parentheses, that's going to reduce nicely. 6 times 1/6 just gives us 1x cubed minus here. What's going to happen to the 6's? They cancel out, so we just have a minus 7. And what else do we have stuck there under the radical? That plus 7. Well, it looks like stuff is starting to cancel. Negative 7 plus 7 is gone. What's the cube root of x cubed? What impact does that cube have on that cube root? It cancels each other out. As a matter of fact, in 1 week's time, we're going to be saying they're inverses. The cube root function and the cube function, when they're performed consecutively, they cancel themselves out, leaving you just an x. Now, just because one direction reduces to x doesn't mean the other direction does. But if they both reduce to x, that means that these functions are inverses. So I'm going to write down the f and g again, just because all those little circles, well, they're not circles, ovals, they start getting messy, don't they? So there and there. Now let's go in the opposite direction. We want g composed with f. That's saying take f and plug it into g. Take f and plug it into g. Can y'all see what's about to happen? We have the 1/6. We're going to replace x with that cube root of 6x plus 7. And we still have a minus 7 over 6. Any questions on my logic there? I'm taking f, plugging it into g, and now it's a matter of simplifying. I see one thing that's about to cancel out. Actually, I guess it's two things. We have a cube root being cubed. What's going to happen?
Lose the square root.
I can't hear you.
You lose the square root.
Okay. So all we have left is that 6x plus 7. The cube undoes the cube root, leaving us just that 6x plus 7 times 1/6. Let's distribute the 1/6. 1/6 times 6x is going to give me just 1x. Now what about 1/6 times 7? What's 1/6 times 7?
7/6.
Okay. 1 times 7 is 7. 6 times 1 is 6. So plus 7/6 minus 7/6. What's about to happen? Okay, leaving us just x. So once again, that means f and g are inverse functions. I will discuss inverses in more detail the next time. Not the next time, 1 week from today. Right down here, there. So f composed with g of x reduced to x. G composed with f of x reduced to x. And yes, they were equal. The mere fact that they're asked it, are they equal, should start making you think, oh, something's going on, they're going to be equal. Because in most cases, they are not equal. They're trying to get you ready for that definition of inverse, which we'll be seeing in 1 week's time. And I think number 12, oh, it's that cut point method. So, any questions? Okay. Okay.